Welcome everyone. Today we are looking into the AWS ecosystem through an architectural lens. Cloud computing fundamentally changes how we design systems, shifting from procuring hardware to composing on-demand IT resources over the internet with pay-as-you-go pricing. When you look at AWS, you aren't just looking at virtual machines. You are looking at a platform with over 200 services. For an engineering organization, this means we can assemble managed services to build distributed, highly available applications without worrying about the underlying physical data center operations. A strong cloud architecture begins with understanding the physical topology. AWS operates across 34 geographic regions, but the critical unit of architecture is the availability zone. A single region contains multiple AZs, and each AZ consists of one or more discrete data centers. For the distributed system perspective, you must build your application to handle AZ level failures. Because AZs are connected with low latency fiber, you can achieve synchronous data replication with single digit millisecond latency. This is how managed services like Aurora and S3 achieve high durability by transparently storing data across multiple AZs. For global users, we cache content using CloudFront 600 plus edge locations by passing standard internet routing and keep the latency extremely low. Compute is the engine of your architecture. Historically, this meant EC2 instances, which are virtual machines in the cloud. Today, modern architecture lean heavily on containers and serverless. If you have a microservice architecture, you will likely choose between ECS, AWS fully managed container orchestrator, or EKS managed Kubernetes. EKS is the enterprise standard if you require multi-cloud portability or deep open source integrations, while ECS is simpler if you are all in on AWS. For event-driven workloads, AWS Lambda removes the need to provision servers entirely, allowing you to run code in response to triggers. We also utilize autoscaling to horizontally scale our EC2 fleets based on demand, ensuring we don't over-provision resources. Choosing the wrong storage layer creates immediate performance bottlenecks and cost overruns. S3 is our foundational object storage, infinitely scalable and highly durable. We use S3 for assets, backups, and data lakes. For cold data, we aggressively tear down to S3 Glacier for cost optimizations. When EC2 instances need low latency, high performance attached disks, we use EBS block storage. If multiple instances need to mount a shared file system concurrently across multiple AZs, we use EFS. For enterprise migration from on-premise, if network bandwidth is a constraint, we bypass the internet entirely and use physical appliances like AWS Snowball or even an 18-wheeler snowmobile for exabyte scale transfers. Your VPC is your local data center in the cloud. It provides absolute network isolation. Inside the VPC, we distribute incoming application traffic across multiple AZs using an elastic load balancer or ELB to ensure fault tolerance. For complex enterprises with dozens of VPCs, we don't peer them one by one. We use Transit Gateway, AWS Transit Gateway, as a centralized cloud router to simplify network topology. If you have an on-premise data center and need consistent high bandwidth connection without traversing the public internet, you provision AWS Direct Connect, a dedicated physical fiber line straight into the AWS backbone. Route 53 acts as our highly available DNS to direct global traffic. Security in the cloud is identity centric. IAM is the core. Every user, service, and application must have explicitly granted permissions to perform any action. For application level user authentication, we use Amazon Cognito. We protect the data at rest using KMS to manage cryptographic keys. And we never hard-code credentials. They belong in Secrets Manager. At the perimeter, we block SQL injections and layer 7 attacks using AWS WAF or Web Application Firewall. While AWS Shield protects against large-scale DDoS attacks, operationally we rely on guard duty to continuously monitor for malicious behavior using machine learning, feeding all insights into a centralized security hub. The days of forcing every workload into a massive monolithic relational database are over. AWS provides purpose-built databases. If you need ACID compliance and relational integrity, Amazon RDS supports traditional engines like Postgres and Oracle. However, at scale, we strongly recommend Amazon Aurora, a cloud-native relational database built by AWS that heavily decouples compute from storage for immense performance. For high throughput, low latency applications like shopping carts and session stores, we use DynamoDB, a fully managed NoSQL database. To reduce read load on databases, we put elastic cache in front of them. And for highly connected databases like recommendation engines or fraud rings, we leverage Amazon Neptune, a specialized graph database. For enterprise data platforms, data is typically streaming in continuously. We use Amazon Kinesis or managed Kafka MSK to capture and process high throughput streaming data in real time. Kinesis Firehose can seamlessly deliver this data into a data lake built on S3. From there, AWS Glue acts as our serverless ETL engine and centralized data catalog, making the data discoverable. We need run-heavy big data processing framework like Spark on Amazon EMR. For complex analytics and structured reporting, the data lands in Amazon Redshift, our petabyte scale data warehouse, and is visualized for executives using Amazon QuickSight. AWS abstracts AI into distinct layers. For data science teams building bespoke models, Amazon SageMaker provides a fully managed end-to-end platform for training, tuning, and deploying models in production without managing the underlying GPU clusters. For software engineers who just need AI capabilities via an API, AWS provides high-level services. You can pass an image to Amazon Recognition for facial analysis or pass a scanned PDF to Textract to pull structured data out of it. As engineering leaders, we are also leveraging AI for developer velocity, using Code Whisperer to generate code and Cloud Guru to find deep security vulnerabilities and expensive lines of code during the CI/CD process. As you move to microservices, you cannot rely on synchronous point-to-point API calls. They create brittle architecture. We decouple components using message queues like SQS, ensuring that if a downstream service goes down, messages are safely buffered. For fan-out patterns, we use SNS to publish an event to multiple subscribers simultaneously. For highly complex multi-step workflows like order processing or media transcoding, we orchestrate the microservices using AWS step functions, which manages the state, retries, and handle errors. Finally, we expose these backend services to the web securely via Amazon API Gateway. Operational maturity requires treating infrastructure exactly like application software. We define our AWS resources programmatically using the AWS Cloud Development Kit or CDK. To automate the release process, we build CI/CD pipelines. Developers push code to code commit. Code pipeline detects the change and triggers the code build to compile the application and run unit tests. Once tests pass, code deploy safely rolls out the new version to our EC2 instances or ECS cluster. This removes human error from deployments and allows organizations to ship features multiple times a day safely. You cannot operate what you cannot observe. CloudWatch is our centralized nervous system collecting logs, infrastructure metrics, and application performance data, triggering alarms if latency spikes. From a security and audit perspective, CloudTrail is mandatory. It logs every single API call made in the account, telling us who did what and when. As enterprises grow beyond a single AWS account, we use AWS Control Tower to orchestrate multi-account environments, enforcing security guardrails automatically. We also use AWS Config to detect configuration drift, ensuring that if someone manually alters a security group, it is flagged and automatically remediated. Let's bring this all together by looking at a simplified social media architecture. Users hit Route 53, which directs them to our application. CloudFront caches static media globally to reduce load. Dynamic requests hit the ELB or Elastic Load Balancer, which distributes the traffic across EC2 instances running our web and app servers. These instances are in auto-scaling groups, expanding during traffic spikes. Our data is distributed user profiles in RDS, highly concurrent feed data in DynamoDB, and social connections in Neptune. When a user uploads a video or an image, it lands in S3, triggering a Lambda function to convert the video in whatever format, while Amazon Recognition recognizes or analyzes the content of an image for moderation. This is how over 20 plus AWS services interact seamlessly to create a resilient, scalable system. To wrap up, modern architecture on AWS requires a shift in mindset. You must assume components will fail and design for resilience using availability zones. Don't force workloads into a single paradigm. Take advantage of purpose-built databases and serverless compute to optimize performance and cost. Above all, automate your infrastructure and deployments. The best way to understand this is to get hands-on. AWS offers a robust free tier, including 750 hours of EC2 and RDS for 12 months, and always free tiers for services like Lambda. So sign up, spin up an environment, and start building. This is the end of the episode. Thank you for watching. If you like the video, please like, share, subscribe, and press the notification bell icon for future updates. This is your host Bhavesh Kumar signing off. Thank you.